Hi, this is Kate Bricker, and this is Physics 2211 Lab 2 Projectile Motion. So the purpose of this lab was to study projectile motion, or an object of a curved velocity, versus our lab last week, which was just constant velocity. So the fundamental physics of this, which I'll talk on later slide, thinking about the forces that are happening on this object, such as gravity and drag, and how that affects the velocity. So our system for this experiment was the ball, and the surroundings were that gravity, drag force, air resistance, and more. Our methods for our lab were that we just took a meter stick, put it against the wall, threw a ball in a curved motion, and recorded that object. So like I said, some fundamental physics of this are Newton's second law, where force equals mass times acceleration, where we got that force by applying the acceleration to that ball. This can be found using the velocity update formula and position update formula shown below that are derived from Newton's second law. And then additionally on this versus the last lab, we have the force of gravity, which is equal to mg, and the drag force, which is equal to bv squared with a j direction. So like before, our lab was very similar. Using tracker, we were able to take the middle of the ball as it went through the object and develop our line and trajectory. So our code was very similar to last time. You can see that we had our initial positions with a y direction and initial velocity with a timestamp of 1/30 seconds, gravity of 9.8, and a drag of 0.24. We just plugged and checked this drag to see where it would fit up. We didn't use any kind of equation to find that specific number. So here is where we actually loop the code. You can see that we're going to 9 seconds, and we have that velocity and position update formula with a timestamp of delta t that just loops over and over again. You can see that our net force, instead of 0 like last experiment, we do have that net force of that gravity, which is mass times gravity, and that drag force, which is that b times the magnitude of velocity squared. So here's the graph based on that code. You can see that our y position goes down over that 9.9 seconds, but it actually goes down to -1 meters, which doesn't realistically exist. You can see compared to our average or an actual data, that ball stops at 0 over that time, but they do look very similar in their line. So comparing that, the trajectory or the x versus y, you can see that the gravity, just the gravity code is very off. You can see it's almost at that -1 meter mark. But when we add that drag to the line, the experimental and gravity plus the drag are very, very similar. So concluding this, just really talking about what it all means, our experiment was a lot more realistic than last week's with the forces of drag and gravity, but there's still all these external forces that we didn't matter, but you can see when we applied that drag, it was pretty close. So terminal velocity is when a falling object experiences like 0 net force. It's almost like that, the 0g concept. If we're looking at this graph, you can see that never happened, because if that were to be 0, then that gravity and drift would have to cancel it out, meaning that the distance would not occur at all because it would be 0 net force. An experiment where you could see this is skydiving, but there's not a lot of real life applications of this. So another idea is like, what if the object were thrown straight up with the same speed? The time to reach the ground would be shorter than it, because we're not going across this x distance, we're just going up and down. You have that force of gravity is the only force that's just bringing you straight down. thank you so much for your time, and see you later.